Okay, we're recording. Cool. This is trippy. All right. Okay, cool. So we're going to do algorithms and big O notation. Yay. Let's see. So we're going to breeze right through algorithms because we've been doing them for literally weeks now. Algorithms are a series of steps taken to solve a problem or achieve a goal. In this algorithm here, we are baking a cake. Yeah, so that's all of the steps that you would take. You would gather your ingredients, you'd start mixing them, you'd put it in a pan, you'd bake it. If it's not done, then you kind of go back, start over, continue baking it. When it's finished, take it out of the oven, let it cool, ice it, and decorate it. And then you've got a cake. That's basically an algorithm. An algorithm is just a set of steps to achieve a goal. Yay. That's algorithms. Big O. So, from cracking the coding interview, Big O time is the language and metric used to describe the efficiency of algorithms. So here you can see a bunch of different types of algorithms and how they perform compared to one another. We'll go through each of them individually. Also, if anyone has any questions as we're going, feel free to butt in, get me to stop. Yeah, we can answer questions. The whole point of this is that we go a little bit slower so that we actually learn things. So what is Big O? Why does it matter? Why do we use it? It's a way to talk about how efficient an algorithm is. We talk about it in terms of runtime. So that runtime is how long we can basically expect an algorithm to run whenever it's actually processing. We can see what makes a particular algorithm faster or slower, and how space efficient that algorithm is. By knowing those things, we make better decisions as we're programming. It allows us to know that, hey, we should avoid nested for loops, or that we should try to achieve a most efficient algorithm so that we can serve users better. So, big idea. Big O measures time complexity and space complexity in an algorithm. And it's always written in, it's how it performs under the worst case scenario. Let's start with the most basic. This is constant complexity. It's O of 1. So you can see that over here. It's just, hey, there's a straight line. It doesn't matter how many inputs you have. It's always going to perform the exact same. The input doesn't matter at all. So you could think of this as like, say you're delivering something in your hands to another person. It's always going to take a consistent amount of time, no matter what the data is. It could be a piece of paper with hello written on it, or it could be like a hard drive filled with movies and video games and what have you. It's always going to be that same amount of time to deliver both of those items because you're physically handing those items to a person. So here's some examples in code. So if we're determining if a binary number is odd or even, because a binary number, to determine if it's odd or even, you're only looking at a single bit in that binary number. Or if we're accessing a provided index in an array. Whether that array is 5 items long or whether it's 1,000,000 items long, it's always going to take us the same amount of time to access the third index of that array. Also, since we have kind of covered stacks a little bit, whenever you add or remove from like a stack, you're always putting something on top. It's kind of like, say you've got like a stack of books. It's essentially like, hey, it doesn't take you any longer to put a book in a stack, whether it's the 5th book or whether it's the 20th book. It's always, oh, I'm adding a book onto this stack that I've got. Doesn't matter if it's here, doesn't matter if it's here. The same amount of time. Also, like the example I gave earlier, whenever you're physically delivering data on like a storage device. So if one item takes 1 second to process, 100 items will also take 1 second to process. It doesn't matter how many items you've got. Here's an actual code example. Here you can see we've got an array, 1 or 2 arrays, I guess. We've got a tiny array that's got 10 indexes in it, and then a very large array with something like 100 million items in it. So it doesn't matter which array we have, whether we're looking at the tiny array or the large array, accessing the 4th index of either array takes the same amount of time. Any questions about the constant complexity? Cool.
Well, I kind of have a quick, so this is just like a single item within that data. So if you wanted to access position 2 and 3, that would be 2 items of access and not within the O1?
So what you're talking, like you're saying instead of like having like array 4, we're doing like array 2 and array 3, correct? Cool.
Yes.
So that's, you're already thinking more advanced. Congratulations. So that would be basically that's called adding something. Adding adding an element on. That's not what that's called. I don't remember off the top of my head. So that is it doesn't change the actual process though. It's still O1. So even though you're doing 2 things in there, basically you're always essentially looking for what is the most basic way we can possibly talk about a given algorithm. So for that particular example, it would still be O1. There are situations where it would change, but for that alone, no, it would be just O1.
Cool.
Any other questions?
I think with the big O, it's just really basically simplifying it to, like, for example, what you were saying, Alan, there was like 2 O1s in that situation, and then you just simplify it to whichever one is the worst case situation.
Yes, that's perfect way to put that. And that's called multi-part algorithms. So that's when you add or multiply runtimes together. That's what you're talking about, Alan. So.
Okay, yeah, that makes sense.
Okay, cool. Any other things before we move on to linear complexity? Cool. So linear complexity is ON. N represents the number of items you're receiving as your input. So if you're receiving 2 items as your input, that would basically be O of 2, essentially. If you're receiving 100 items as your input, it's essentially O of 100. So but n is just how we simplify it to talk about any number of inputs that an algorithm could receive. Here is the big picture of ON. So as the size of the input grows, the processing time for that algorithm will also grow at the same pace. So they're in lockstep. As input grows, your runtime also grows. Let's see. So O of n is efficient. It can also be even more efficient than O1. But eventually, no matter how large the constant is or how slow the linear increase is, your constant will eventually become more efficient than your linear. So these are things like searching through an array. Remember, we're always talking about big O in the worst case scenario. So if you're searching through an array and you're looking through an item in that array, it could be the last item in that array is the one that you're looking for. So it'd have to iterate through that entire array to find that item. So that's what makes it a linear complexity, even though you could potentially, and oftentimes would find it before you'd actually reach the end. It's also if you're performing an action on every single item in an array. So like, say you're taking an array and you're adding 1 to every single thing, it'd be ON. Whenever you're inserting an element into an array, whether you're, so like say you're sorting something, or you're inserting something based on like an alphabetical order. That thing you're inserting could go at the end, potentially. So that would be O of n. It'd also be like downloading something. So like back to our previous example of constant complexity, where if I'm just like delivering data to you, that comes all at once. If you're downloading something, that comes to you over time. That also kind of leads back into times that linear complexity can be faster than constant complexity. So like if I were to write hello on a piece of paper and then hand deliver that to Alana somewhere, then that's going to take a lot longer than if I just type hello in Slack and send it to her. So that would be an example of when linear complexity would be better than constant complexity. If one item takes 1 second to process, 100 items will take 100 seconds to process. So here's an example in code. Here we're making 2 arrays. Once again, we're making a tiny array and a large array. They're all filled. And we are, what are we doing with this array? Oh, we're finding a random number inside of that array. So this would be basically a search. So what we've taken in, we're basically finding a random number within that, and then we're iterating through that entire array. And then once we find it, returning. That item could be the very first item in that array. It could be 0. The random number could also be, in the case of our super large array, up to something like 90 million. It would take a lot longer to search through that. So that leads us into talking about scenarios. Oh, before we move on, sorry, does anyone have any questions about ON? Cool. So some scenarios. Basically, when we're talking about scenarios, we're talking about one of 3 potential outcomes, or one of 3 broad categories of outcomes, I should say. So we've got our best case. So that's an algorithm that, like, hey, it gets real lucky, and that random number that we picked, it was 0 in this last code example. That random number was 0 that it picked, and it's going to find that the very first the very first key of that array. So while it's good to know what a best case would be, it's not very useful in practice because lots of algorithms can just get lucky like that. And that's not really going to be an expected outcome. It's just going to be you happening to get real lucky. We've also got expected case. So this is more the real world performance that you can expect from an algorithm. This is really used to differentiate between different algorithms. It's whenever you've got 2 algorithms that perform very similarly, they work in a similar function. It's very it's easiest to compare them using their expected case. Whenever, like, the worst case would be the same, or if their best case is the same, we would switch over to looking at those using their expected case. The worst case, this is how we express performance of algorithms in Big O. So in a lot of algorithms, particularly like sorting algorithms, the worst case scenario and the expected case scenario are exactly the same. A lot of that happens because a lot of sorts will have to go through each individual item in their set to be able to declare, hey, I've sorted what you've given me. So that's why that happens. There are some that do perform better, have a better expected case than a worst case, but that's not for today. Okay, let's talk about space complexity. So most data structures, arrays, lists, anything that you'd put data into, like a tree, anything like that, will have it takes up a space according to how large that given data structure is. So if you have 3 items in an array, that data structure is going to take up that according amount of space. It's going to increase as the number of items that you put into it grows. Space complexity and time complexity are different. Each algorithm may have a different space complexity from a time complexity. Some do have the same, but most of the time they're different. Does anyone have questions on complexity or space complexity and our different scenarios that we've got? Cool. So now I'm going to move into O log n. So this is logarithmic complexity. With O log n, the idea is that as the amount of inputs that you're taking in grows, the runtime of processing that will increase by half for each input, for each new input that you receive. O log of n is super useful. You can do really complex stuff really quickly. A lot of recursion algorithms are O log n. So not a whole lot of examples with this, but like any kind of tree data structure where you're searching through a tree and you're eliminating half of the results in that tree for each search that you're doing would be an example. Since I don't want to actually get into binary search trees, if one item takes 1 second to process, 100 items will take 3 seconds to process. That's the power of O log n. So back to our code. As I was saying, I don't really want to get into binary searches. Here is an example, though, of kind of the performance you would expect from a log n algorithm. So like here, basically we're taking in a very large number, like 16 million, and we're able to reduce that by half every single time that we are going through, that we're iterating through this. So we're eliminating half of the potential results in every iteration. So we're able to reduce our huge number, our 16 million results, down to a single result in only 24 iterations by looking through it this way. So this is essentially what a binary search tree does. It's just without all of the binary search tree code. Anyone have any questions on log n?
Would it be effective to describe log n as being binary?
I don't believe so, but I'm not 100% sure, to be honest with you. So,
okay.
Google it.
Good answer.
So they were
So it's
saying
also-
that the binary search is the classic example of the O log n.
Yeah. Yeah. So that's really the best example I can give without like going super into something I don't want to get into. So this is enough to grasp this for now, and it's something that we'll see later as we do more CS stuff. So what were you saying, Crystal?
Is it also like if you're splitting the array in half and like searching in the halves, or
Yeah.
like?
Yeah, that's exactly what this is doing. Yep.
Okay.
Anything else? Cool. So let's do quadratic complexity. This is n squared. So we know this from like nested for loops, stuff like that. Each time the input grows, the runtime increases exponentially. You should avoid using this. I also have a typo on this screen, so please ignore that. It should not be O log n squared. It should be just O n squared. Cool. All right, so here's some examples. Lots of sorting algorithms have a quadratic complexity. So you'd see this in something, I believe, oh gosh, I should not have started saying that sentence because I don't know how to finish it. We'll cover that in a second. So if you'd perform an action on every item in a 2D array, that would be a quadratic complexity. Also, if you're searching through a 2D array, remember, we're always talking about worst case scenario when we're talking about big O. So whenever you're searching a 2D array, the item you're looking for could be the very last item in that 2D array potentially. So that's how we would talk about it and how it relates to our big O notation. If one item takes 1 second to process, 100 items will take 10,000 seconds to process. You can see why you don't want to use this. Most items won't take a whole second to process, but you can see how, like, even if you have something that takes, you know, a literal microsecond to process, once you have 1 million items that you need to do that with, it's going to quickly become just unreasonable to use because you'll be waiting forever for anything to happen. So here's a code example. So for this, we're iterating through an array with our first for loop, and then we're also iterating through that same array inside of our second for loop. So you see on the right are console log outputs that we get from doing that. So even though we've got 5 items in our base array, we're still getting 25 outputs from it. Not great. Anyone have any questions on n squared?
Yeah, so basically when we're doing our daily code, I was like, man, we've been doing that all along.
Yep.
Oh yeah, the last two. Better to find. We need to find ways to avoid them.
Yep. And that's, you know, like, that's the whole kind of point of Big O, is so that, hey, we can look at algorithms and see, hey, we shouldn't be doing this. Like, unless we absolutely can't get around it, we should be doing something different. So there are situations where you'll have to do it, and that's cool, but think through it before it happens. Let's talk about factorial complexity. So this is n factorial. This is O factorial, or n factorial is basically not used. Basically, it would be like throwing up a deck of cards into the air, and then they miraculously all land in order on the floor. That's what you're doing whenever you're doing n factorial. You should know that it's there. It doesn't, you'll never use it. I don't know. We still cover it though. So yeah, it's there. If one item takes 1 second to process, 100 items will probably take a very long time to be processed.
To infinity.
Yeah. Okay, so this is basically everything that I've got for today. I don't want to overload this, so I think I'm going to, well, I know that we need to split this up into 2 things. So I'm going to do another thing on Big O tomorrow that will kind of cover everything that was left out today. This is basically the GA module that we've gone through. The GA module has like 1 extra thing in it, which is actually, I think, it's not what Alan asked about, but it's kind of related to what Alan asked about. So, and it has to do with dropping constants. So we'll get to that tomorrow, though. No worries if you can't make it, we'll record that one too. Or if no one comes, I'll just record myself talking to a wall for an hour. So this is basically what you should be taking away from what we've gone over today. So we've got constant complexity, linear complexity, logarithmic complexity, and quadratic complexity. Those are the 4 big topics. If you're confused about any of that, go look at the GA module, go find additional resources somewhere. Yeah. Ask me.
Are we gonna do the examples?
The examples for...
Well,
What?
there's a list of examples, like, I guess just labeling them which ones they are.
Oh, yeah, we can do that. From the GA module, you mean?
Mm-hmm.
Yeah, definitely. Yeah, we'll go through and do that. So here is a little bit more of what you should take away. Factorial complexity exists. We also have best expected and worst case scenarios. So if you're not clear on those, go back, look at them. Same thing with space complexity. Space complexity is a little bit hard to like wrap your mind around because it really depends on, like, you have to look really hard at the code that you're looking at to be able to understand space complexity. But it's something that you should definitely delve a little bit deeper into. So like I said earlier, this is the most basic stuff that we can do. I wanted to, at least introduce this stuff so that we could understand the very basics. So for tomorrow's stuff, we'll talk about dropping constants and non-dominant terms, also adding and multiplying runtimes, and variance on different log and runtimes. So like, this is probably enough to maybe get a job, potentially, just knowing these basic things. But if you're ever asked anything even a tiny bit more advanced than this, you'll probably not understand what's going on. So I'd really recommend looking over what I'll have tomorrow also. That's it. Let's see. Let's go over some GA modules. Go through this. There is a good chart in here. What is this, 22? It kind of does what I did for like the big header sections, but it tells you, hey, if this takes 1 second to do, this is how long all of these items potentially would take. Like if you've got 600 items in a quadratic complexity, then it's going to take 360,000 seconds. Let's see, what is, okay. Those are in slides. This is the one thing that we didn't cover today. I'll get to that tomorrow, though. Let's see. The examples. Where are the examples? Does anyone?
They're on the GitHub Enterprise.
Of course. Give me 1 second.
I just pulled it up. Oh, you got it. Okay.
Cool.
You're so fast.
Exercises. Okay. Is there answers for these? Because I have not looked over them. We can find out. Of course.
I don't think so.
That's cool.
Because it said that, oh, we'll go over it in class, what the answers are. So.
Cool. That's useful.
But we can all, you know,
we can
talk
all
about them.
Out. Yeah, we'll talk about them. I'll bring some more examples tomorrow too, once we introduce a little bit more complexity. Also, the examples I have are just a tiny bit more complex. So, but these are good to get started. Good to cement what we learned today. Okay. So, how do we want to do this? Does someone just want to volunteer to answer number one?
Sure. I'll go.
Go ahead.
Since there's a for loop and it's iterating each one, I'm going to say maybe it's the linear. Hold on, but then it has an if statement. Yeah, maybe it's ON. Maybe it's linear.
Yeah. So this is it's ON. So and we'll get into this a little bit tomorrow. Like I'm kind of surprised the GA module doesn't touch on it at all, especially when it's giving examples like this. But whenever you're doing you're doing basically a constant thing, but which is the if statement. But you're doing it alongside a linear thing, which is your for loop. So you're always going to basically simplify it to its most complex form, because that if statement doesn't really impact the big number a lot. The big thing we're looking at, if we increased this phrase up to 1 million characters long, then our little baby if statement that's a constant complexity thing doesn't really matter anymore. What really matters is that we're doing our for loop for each split that we've done in that phrase. So that's what actually takes the most amount of time. It's the most complex thing in this algorithm. So that's what we actually talk about, essentially.
Right. So like it said, we're looking for the worst case, right?
Yep. Exactly. Anyone want to do number two?
Looks like a quadratic to me. Got 2 for loops.
Yep, sure
tip
does.
off.
Yeah. Yeah, that's correct. I will say we'll touch on this a little bit tomorrow, but like I know a lot of interviews from what I've read will throw something like this at you, where you've got nested for loops, but they're actually with separate arrays. So like you'll have array 1 and you'll have array 2, and it's nested. You've got that nested for loop, but that is actually ON instead of it's a linear instead of the quadratic, like dealing with a nested array would be. So that's just something to look out for. Like I said, we'll cover that more tomorrow.
Yeah.
Way ahead. But
Watch out for those trick questions, huh?
yes. Yeah. You can't just look and see, oh, it's 2 for loops and be like, oh, that's instantly like quadratic. You gotta look at it a little bit more, but yeah, that's good instinct. And I don't think there's anything in here that's even that. Yeah. Yeah, there's no examples of that in here, but I know it exists. So, number 3.
That would be factorial, isn't it?
What was that? What else? I believe so.
I mean, it's also labeled factorial.
Yeah, it's labeled that, but I don't know if that's what the code is actually doing.
Well, we can always ask for the solution from Lele later and check our answer.
Definitely. I think you're right, though. Like, it's called factorial. I'm going to assume it's factorial. That wouldn't be my first instinct, but I would assume.
Well, it looks like that because I'm guessing the factorial. Yeah, it's confusing because of the -1, but I was guessing it was factorial as well.
Yeah. I'll ask about it, but because of the multi. Okay, never mind. Yes, that's factorial. I'm sorry. Cool. Number 4.
That's a 1.
Yep, sure is. Look at that. Good job. 5.
Linear?
Yep. That would be linear, I believe. We'll also cover this a little bit more tomorrow, but whenever you've got, like, essentially you've got 2 loops there. You've got like a for loop and a while loop. So, like you're doing 2 things there. So you would kind of assume it would be like you would add those together. I don't believe that that's the case, though, in this instance. But like I said, we'll talk about more of that tomorrow. 6.
Is that logarithmic? Because it looks like the modulus is then. Whoa. Now I'm confused on it. It might be linear, actually.
That's my guess too. It's linear.
I think it's linear. I don't see anything there that would make it logarithmic, because the modulo doesn't really impact the runtime in that way. So, two more. 7.
Is that another linear?
I was thinking that would probably be more quadratic, but I can't explain why that would be what I'm thinking.
It would be quadratic, linear, because you've got 2 loops there. So you've got the for each loop, and then you've got a second for each loop. They're not nested or anything like that, and they're not manipulating the same data. So, last one, number 8.
It looks like another linear. I don't.
That's also my instinct.
Yeah, me too.
It's not doing anything to the data. It just is running through the I++.
Right. Yeah, I think the numbering kind of throws you off a little bit, but yeah, I think that would be linear also, I believe. Cool. Well, that was a nice tidy hour. Does anyone have any other questions? Anything we went over? If you have any other stuff later, let me know.
That was really good and very purposeful. I like how you had that slide, so it's very purposeful.
Yeah. Felt like if we're going to do this, we should do it right. I was so miserable writing this last night, but it was like, oh, I'm learning this. I guess I kind of understand it now. Like I said, we'll do a little bit more tomorrow where we're adding on to this. So if there's anything you didn't get from what we did today, let me know. But yeah, it only gets harder from here. So.
Yeah, I've got recursion on Thursday.
Yeah.
You.
So exciting.
And I think that's one we desperately need with all of our habits of doing nested for loops.
Get logarithmic notation. Get some good stuff.
Yeah. I don't know. I feel like we breezed through this super fast in GA, but like every single thing we did for the rest of the CS stuff, Bill was like, oh, what's the big O of this? And I was like, I don't know. Like, we did that in 30 minutes on one day. Like, I don't know any of the big O stuff. So I felt like it would be beneficial to like do a little bit more for Big O than we necessarily will for most of the other ones. But and it seems from just looking at like what little interview stuff I've seen so far, it's like, oh, what's the Big O of this? It's like, oh, what's the runtime? Like, no. So.
Well, and that might be good, like for us to just kind of practice, like when we're going through the other, CS stuff and daily code challenges too, and just kind of like reviewing that on top of it, just like, checking in, like, okay, what.
Yeah, definitely. And like the GA modules do like a pretty good job at like still bringing that stuff up throughout all of them. So as long as everyone else is kind of at least following the GA stuff a little bit, then like it should continue to come up, but we'll see. Hopefully everyone presents well.
And all of this stuff is on in cracking the code interview as well.
Yes. Yeah.
And there's like dedicated chapters or sections for all of these things.
Yes.
So that's a good place to go for
that
more
is
info.
that's where I got most of this from, is from that book. So there's also over here, I sent this out. This is basically everything in all of these slides. So like the quadratic complexity. So if you like basically need any of the slides, it's just part of that link. There's also additional resources. This is essentially everything that I pulled from for all of this. So if you look through those, you should be good. This Big O cheat sheet, super useful. It's got all of your different algorithms, how they perform, their average, their worst, what their space complexity is, all that stuff. So highly recommend this. Super useful when you're trying to pit like one sort against another sort. So all right, anything else before we go?
So is David, is there a way we can use this room after we're done? Maybe
Yep.
like take a few minutes break and then just get back again.
I'll start up a new meeting in the general area. And
Okay.
All right.
All right.
Yeah,
Thank you.
that sounds good.
of course.
So noon. Let's regroup at noon.
Okay. And I have a meeting with Aaron at 12:30, so we can kind of make this a brief, just kind of introduction and brainstorming, and see what we're interested in. If that works for you guys.
Yeah, that sounds good.
Cool. All right. See you at noon.